students, it is now unfair to you if I not discuss Newton's three laws conventionally, because you have came across 2 or 3 chapters, I think, that is, one is vector, another is one-dimensional motion, another is unit dimension, etc. etc. These are very fundamental and basic things, but unfortunately, or you can say fortunately, this is your first study of fundamental of law of nature. You don't have any law till now which is actually the law of nature. All the chapters that you have studied till now at your standard, and what I have discussed in this lecture series also, that are fundamental, that are mathematical, actually mathematical tool, you can say, to understand the law of nature or the law of physics. And this is what we are going to start first time, a very important law of nature in the form of Newton's laws of motion. And before going to the Newton's law, the statement of Newton's law, which was published in the famous book Principia Mathematica in the year 1687 as a law of inertia. But before this publication of this law in this systematical way, there are a lot of contribution from the ancient time, which was started first by the great ancient philosopher, the Greek philosopher Aristotle. And first he want to study the objects, the motion of objects in a systematical way, and he have seen around us the bodies, the objects which are moving in various pattern, which are at rest, sometimes they are moving, and he just want to study all these things systematically, and what are the law governed and the behind the motion of these objects, what are the law behind the motion of these objects, he just wanted to study. And he just observed and find some basic laws, and what he have observed at that time just stated as a law. And at that time it was very difficult that someone was started to thinking that how the laws of nature are actually evaluated, or how the God play the game. Okay, according to Feynman, you know, Feynman said these laws of nature, that this is a game of chess. God played the game of chess, and just seeing the game, we just want to find out the rule of the game. This is the law of nature, and that laws of nature are the rule of the game, you can say, are actually from the ancient time people wants to find out. And the first attempt, I think, from the various resources I have found that it was Aristotle, and he saw the living or non-living thing. Mostly the laws are first times given for the non-living thing, of course, but it is equally applicable for living system also. I will tell at the last of this video that it will also be applicable for the living system also, but there is some restriction. You know, the living systems can do some more activity than the non-living system, so we can understand the law or the rule, rules how the nature is played, so we can easily understand to the non-living objects. So the first attempt was obviously for the non-living system, and you can see also now, if you imagine that if you imagine that there is no science now, even now, if you imagine that there is no science, there is no laws you have, okay, then how can you state the motion of the object? Whatever you have seen, whatever in your surroundings, then you just want to unify all the things in a single statement, want to unify all the things in a single statement. And Aristotle wants to do that only. And first he said that the heavy objects wanted to be at rest. As we all know, we have seen that the big rocks are on the earth's surface, they are at rest. So just seeing that, just observing the system, There was no tool, please keep in mind, there is no tool to analyze these things in other words, in other way. There is no scope of experiment like in present day. So at that time, the only thing was our eyes and our brain, the most important thing, that is the human brain. So he just saw the surroundings and he found out that the heavy objects are at rest on the earth's surface. So he just stated that heavy objects wanted to be at rest on the earth. And light objects like smoke, so light objects like smoke wanted to be at rest in the sky. So whatever he saw at that time, whatever he observed at that time, stated as a basic rules, stated as the natural state of the objects. So the first statement was this, that the heavy objects wanted to be at rest on earth's surface and light objects like smoke wanted to be at rest in the sky. Now the questions arise for the stars, for the celestial objects. How the first statement is contradicted? Here it is said that the heavy objects wanted to at rest on the earth's surface. So the question is that what about stars? They are also heavy but are not on the earth's surface. So he stated that stars wanted to remain in the heavens. They are celestial objects. So they wanted to remain in the heavens. Now the next question is that what is this is the position actually. The statements, first two statements are actually the positions for the light objects and the celestial objects, or the heavier objects also. And in the heavier objects there is a category that is the celestial objects. So celestial objects are supposed to be at heaven, in the sky. Now the second thing is, what about the moving object? So again he used the daily life experience, and if you move an object, if you push an object on the floor, you can push a ball and the ball will be at rest after some time. So by seeing this phenomena, this kinds of phenomena, that any moving objects will be moving, if you push then it will be at rest, it will be stopped at some later time. So with this observation he stated that a moving body in a straight line will come to rest due to its natural tendency. So he now stated for the moving object that it is a natural tendency of a moving object that it will come to at rest after some later time. Okay. So the conclusion of that is all the moving bodies will be deaccelerated. If the moving body will be at rest after some time, then the conclusion is that the object which will be moving will be always deaccelerated. But the question is asked then, why the object which is falling vertically, why its speed is increasing? So it's the question. Then the next statement is that the objects closer to earth will be moving faster. So can you imagine how much statements are required just to find out the law of motion of a simple, you can say, simple objects around us. So there need several statements, but we are always try to find out the single statement for a particular case. That is, the work of this great scientist was always to unification the statements, to make unification of the statements. So now Galileo Galilei have done the job. What he realized first, this was the only person who realized first that the force is necessary to change the velocity. It is not the natural tendency of the objects that in a moving, when the object is moving in a straight line, it will come to a rest, or it will stop some later time, and the object which will moving towards the earth, it will accelerate, that is, its speed will be faster and faster, as stated by Aristotle. But Galileo Galilei first realized that it is not the natural state like that. Whenever there is a change of velocity, there is need of force, and it's a natural tendency of an object that it wants to be, or it wants to remain its initial state, that it cannot change its initial state. Otherwise, if we apply some force, some external force, some external influence, if we don't give some external influence, then it's a natural tendency of an object that it will remain in its initial state. It's want to persist its natural state. And that state and that property, actually, the property of the object is called inertia. And the name inertia was first given by Johannes Kepler. He stated that the tendency of objects to persist, change in motion, is called inertia. And these two statements, the realization of the force and the natural tendency of the object named as inertia, together give rise to the Newton's first law. Newton just unified this statement and give a law in a systematic way called law of inertia, and he published the law first time in 1687 on the book Principia Mathematica. And as usual, he gave the total credit to Galileo. So sometimes the first law, that is the law of inertia, is called the law of Galileo. It is nothing but the statement was nothing but about the law of inertia, that any object try to remain or try to persist its initial state, otherwise extra force or the external influence is not given. And the statement was, if there is no external force, the rest object will be at rest, because this is its natural state. When the object is in rest, it is in initial state. So due to inertia, it wants to persist in its rest state. So if there is no external force, the rest object will be at rest and the moving object will continue. The moving object will continue to move in the same path, its motion in the same direction as before. So this was the statement, conventional statement of Newton's law, which is known as the law of inertia. And Newton was mostly influenced by the great Galileo Galilei and Johannes Kepler. Johannes Kepler just give the name inertia, this natural tendency, but actually this tendency or this inertia is first realized by Galileo Galilei. And this first law of Newton's, the outcome of this first law of Newton's are the definition of force. First, we are able to define a force in a systematical way. Then what is actually mean by force? A force is that pushing or pulling which changes the state of motion of the object, which changes the inertia of the object, which changes the initial state of the object, which acts opposite in the inertia, the property inertia of the object. And at the same time, we are able to define the inertial frame of reference also. And what is inertial frame of reference? Inertial frame of reference is that where the Newton's first law is valid. It's as simple as that. If you push a ball on the floor, and if the ball is moving, and if it will continue to move, if you neglect the friction, and if it will continue to move forever, then this floor can be treated as the inertial frame of reference. So the outcome of the first law of Newton, which was actually formulated from the time Aristotle, and took a long time to formulate this statement. And from this statement, we are able to define the force. We are actually know the property of inertia and also the inertial frame of reference. And what was the assumptions that are made on this kinds of observations or these kinds of experiments, you can say? What are the assumptions they have done? At that time, it was not known, but now it was known, and we can tell that the discrepancy of these statements are assumptions at that time. And the assumptions are space is Euclidean in nature. The space is flat and infinitely extended, and it obeys the geometry of Euclidean. But in real, this is not obviously an Euclidean space. Okay, but this is I cannot explain this in this position, but it is sufficient to say that the space is not actually in general Euclidean. But in Newtonian mechanics, It is assumed that the space is Euclidean in nature, space is flat and is infinitely extended. And another important thing is that time goes from minus infinity to plus infinity with uniform rate. So there was a space-time assumptions on the Newton's laws. And the Newton's laws are only valid if we assume these two assumptions. The space is Euclidean in nature and time goes from infinite past to infinite future in uniform rate. Then only we can use this statement, and it is obvious in our real world or the macroscopic world where the Newton's laws are applicable. You can use this. And there is also assumption there is homogeneity of space. We will talk later on about this when we talk about momentum conservation. So momentum conservation actually comes from directly. The momentum conservation is directly the consequence of the homogeneity of space. I will tell you later on. But these are the assumptions and this is the law. And the background is this. And now I want to generalize this law for the living objects also. So in general, you can state the Newton's law, Newton's first law like this. Every natural system has inherent tendency to maintain its states unless it is subjected to an external influence. For any living or non-living system, even for human being, we always want to maintain our inherent tendency if there is no external influence. I can give you an example that at the very early morning, you don't want to wake up. Why? Because it's your natural tendency. If there is no external influence, if there is no work in your hand, then obviously you want to lie on the bed because it's your natural tendency. It's a Newton's first law. But if you have some external influence, then you will wake up very early. And it will depend obviously how much external influence are there. If there is a job interview, then the external influence is more and more. If there is a class, then I think the influence will be something less. Okay, if there is an exam, then the external influence is little more. So, depending upon the external influence, your natural tendency to persist your initial state will change. So, it's not only for the non-living object, but it's equally true for the living objects also. And in general, you can state the Newton's law as every natural system has inherent tendency, and this inherent tendency is nothing but the inertia. So every natural system has inherent tendency to maintain its states unless it is subjected to an external influence. And this external influence is, in physics, systematically known as force. And this inherent tendency in physics is systematically known as inertia. So the Newton's law, the Newton's first law, is not only for the non-living objects around us, it is equally applicable for the living objects also, for you and me also. That we all have a natural tendency to persist our initial state. And if there is no external influence to us, we are not doing anything. Okay, so this is all about the Newton's first law. Thank you.